Okay, I'm very pleased to welcome you in this webinar. Please check that your microphone is on mute. I will start by introducing myself and the project also. So I'm Linda Tomasini from CNES, which is the French Space Agency. And I'm in charge of capacity development activities at CNES, especially with Africa. And I am the coordinator of a working group called Working Group Africa. Let me explain just a little bit what this working group is working on. Actually, the Working Group Africa was in charge of training of trainers program being funded by the European Commission. And it's a joint effort of 12 institutions from 8 European countries, aiming at training at least 20 African trainers to the use of Copernicus in 3 languages in 16 African countries. So the project, I should say, it has started already 3 years ago, and it has been completed just last month. And so we have actually trained 20 African trainers in French, in Portuguese, and in English to the use of Copernicus data. These trainers, they have trained themselves local trainees, reaching out to more than actually 2,000 trainees in the different countries. So our objective is to develop the network of Copernicus relays and academies in Africa, and to raise awareness regarding Copernicus in Africa. And so the webinar that we're organizing today is a follow-up activity from this project. One thing I would like to say also is that we have developed training content covering all the topics that you can see on the slide here. One module address a specific topic, starting with trainer methodology also, because the objective is to train trainers. We have addressed also GIS basics, remote sensing and optical data processing, the presentation of the Copernicus program, how to use the Python and Jupyter notebook for the purpose of application development based on Copernicus processing. There's also a module dedicated to SAR radar data, a module dedicated to artificial intelligence for Earth observation data analysis, another module for web mapping, and also we have a series of thematic trainings covering different themes such as forest monitoring, disaster management, agriculture, and so on. And so the training content is hosted on a digital learning platform. And this digital learning platform is open to new users. So if you want to access the platform, you just have to send us a message with a motivation letter also. And we will be happy to welcome you for the use of this platform. Okay, I guess that's all for me. So it's time now to let the floor to our speakers, and today the webinar is dedicated to the topic of forest monitoring, and we are very pleased to welcome Professor Thuy Le Toan from CESBIO GLOBEO, who is the prime investigator of the biomass mission. And also we will be welcoming Stéphane Mermoz, CEO of GLOBEO, and he will introduce to you the TropiSCO project aiming at monitoring the tropical forest thanks to Copernicus data. So I will let the floor to Dr. Thuy Le Toan. Thank you very much, Thuy. So I will stop sharing my screen and you can start with your own slides. Thank you very much.
There's some change. Stéphane Mermoz, GLOBEO, will start first because
okay, sorry, there was a mistake from my side.
No problems. No problems. Thank you very much, Linda and Cecilia. So can you see my screen?
Yes, we can see your screen.
Yes, you can see the screen.
Okay.
Thank you.
Thank you very much, everyone. I'm very pleased to introduce you the TropiSCO initiative, led by GLOBEO, CESBIO, and CNES, and funded by CNES and the French Ministry of Europe and Foreign Affairs in the frame of the SCO, the Space Climate Observatory. This initiative started in 2021 and is still ongoing. As you may know, deforestation globally is far from being over. Here you can see the figures of the Global Forest Resources Assessment from the FAO, and you have for each continent, Asia, Oceania, or Europe, Africa, and so on, the forest area net change from the 90s to 2020 in million hectares per year. And you can see that in Asia, Oceania, and Europe, and North and Central America, for example, we have a small gain in forest cover, but this forest gain is mainly driven by forest plantations. You can also see that in South America, we had a huge amount of deforestation in the 90s and in the year 2000s, and that this deforestation has decreased between 2010 and 2020. And in Africa, we have an increase of deforestation from the 90s to now. The deforestation is increasing slowly but surely, and mainly driven by plantations as well and selective logging, for example. And as a reminder, of course, forests act as carbon sinks, slowing climate change, and deforestation release carbon into the atmosphere, and climate change is making forests even more vulnerable to stresses such as forest fires and pests and so on. So it's an ongoing problem. But deforestation can be curbed with satellite alert systems and political actions. This is here a notable example in Brazil. Here you have the deforested area in Brazil in square kilometers from the 90s until now. And you can see that when Brazil decided to set up a satellite alert system called DITER, which was the first one actually in the world in the past, and together with political actions, Brazil succeeded in reducing deforestation from the year 2004 to 2012, approximately by 75%. So it's a huge decrease in deforestation. So it was a success. And after that, many countries, such as Peru, for example, and other countries, decided to set up as well a satellite alert system. But one of the problems with such system is that clouds may delay timely detection in the tropics. Here in this figure on the right, you have the number of valid Landsat images in Brazil from 2014 to 2019. And you can see in red that in some season, especially the wet season, for example, between January and March or April and June, we have areas where we never have any clean optical images. Optical images without any clouds. So to tackle this problem, we can use radar images because, first of all, because radar can see through clouds. So you can see here that in addition to seeing through clouds, radar penetrates forest and then can bring information about, for example, forest biomass. Thuy Le Toan will talk about this after this talk, but can also detect deforestation. Here you have an example in South America, in French Guiana, near the equator, near the town of Maripasula, where we almost never have any optical images without clouds during the year. So that's one of the reasons why radar is welcome in this kind of country. In Gabon as well, we have many Sentinel-2 images with clouds and other countries near the equator. The problem is our radar and in particular Sentinel-1 at C-band, Sentinel-1 based deforestation detection is not straightforward. Why? Because the Sentinel-1 backscatter is sensitive to environmental factors such as soil and vegetation moisture, topography, is sensitive to forest characteristics such as tree height, biomass, canopy density, and phenology. Of course, if you set up a deforestation detection system, you have to deal with Sentinel-1 orbit, such as a descending and ascending path, and Sentinel-1 incidence angle. The backscatter is different with the type and intensity of disturbances, and also the backscatter is very sensitive to remaining vegetation on the ground and surface roughness. So if you log a forest, you will have very different backscatter values if you leave remaining vegetation on the ground, or if you clean the ground very quickly after the deforestation event. So you have to take into consideration all these factors to set up a detection system. But we have a good news is that we still have a consistent drop of SAR backscatter over deforested areas, especially over dense forest. So this is an example of temporal backscatter evolution in time over first over a forest canopy without any damage here, and then with a backscatter event. So first we have a forest canopy, you have a rather stable signal, and then you have an initial degradation here. This is the event number 2 in October 2017, where some tree trunk and trees are remaining on the ground. And then here we have fire to remove vegetation on the ground. And then you can see a drop, a decrease of backscatter. And then after that, we really have the like what we call the deforestation event. And then the pasture, in this case, or culture, grows again with increasing precipitation. And then you have an increase of the backscatter signal. And finally, in 18, you have the pasture, the grass that reaches few centimeters height, like 10, 20, 50 centimeters height. And then you can see that the signal almost reaches the same values as before when we had intact forest. So you can see that we are sensitive to deforestation, but we are also very sensitive to precipitations or the increase of grass and so on. Because the radar backscatter is sensitive to deforestation, some few deforestation system detection were developed in recent years. We have TropiSCO, for example, based on Sentinel-1 ascending and descending data with a temporal resolution of 6 to 12 days, depending on the availability of Sentinel-1 images, over 9 countries. And one of the particularities of this system is that it's adapted to the country specificities, like forest definition and so on. So I will come back to this later on. We have other systems such as, for example, DETER-R in Brazil. It's really dedicated to Brazil. We have the RAD system developed by the Wageningen University in the Netherlands that is developed over 54 countries. It's available on the Google Earth Engine platform, and it's a system that is uniform across countries, meaning that this system is based on a forest definition selected. I mean, the same forest definition is applied to all the countries, all the considered countries. So, and we have a Japanese system, GGFast, developed over 77 countries, and it's the same as RAD. It's uses a uniform forest definition, and the temporal resolution in this case is 42 days. And TropiSCO is one of these systems. It's a continuous deforestation monitoring system. So based on every single Sentinel-1 image that is acquired, over 9 to 10 countries so far. So using the forest definition of each country, we have the detections from 2018 to now with a pixel size of 10 meters, a minimum mapping unit of 0.1 hectare, meaning that the minimum area detected on the ground is 0.1 hectare. And the deforestation detections can be used to detect, for example, illegal activities such as illegal gold mining and so on, management of protected areas. It can be used to monitor conservation agreement such as REDD+ or EUDR, and can be used to enforce the certification labels such as zero deforestation and so on. So far, we applied the system over Brazil, French Guiana, Suriname, and Guyana, Gabon in Africa, Thailand, Vietnam, Laos, Cambodia in Southeast Asia, and even in temperate forest. I will show you an example. So, regarding the process, every night the TropiSCO processor processes new satellite images on the CNES supercalculator facility, the CNES HPC, and detects new deforestation area and automatically updates the forest loss maps and statistics and transfers the products online to a WebGIS on the tropisco.org platform. I will show you this later on. This is a process that is fully automatic, and the same algorithm is applied over all countries with sometimes some small specificities regarding country needs. So this production is fully automatic. Of course, we cooperate with country. Actually, we don't map the countries if there is not any cooperation with the countries. So, for example, as notable examples, we collaborate with the VNLC in Vietnam, which is the Vietnamese Spatial Agencies, and also the Forest Agency of Vietnam, FIPI. We collaborate with GISDA in Thailand, Thai Spatial Agencies, with AGEOS in Gabon, with ONF in French Guiana, and so on. And one of the most notable cooperation is with INPI, the Institute of National Pesquisas, that's in spatial research in Brazil. So Brazil had an operational deforestation detection system based on radar called DETER-R. And in the last years, we cooperated with Brazil, with INPE especially, to fuse both systems, DETER-R and TropiSCO, and to create an even better system called DETER-RT. We took the best of the two systems to create a new system, DETER-RT, that is actually now operational in Brazil since a few days. This is very recent, and this new development will be showed in the COP30 in Amazonas, that is actually right now, and this system is really dedicated to deforestation in Brazil, to the need of Brazil. So in Brazil, to curb deforestation in Brazil, alerts should be, of course, accurate and actionable, but especially it should be linked to a law enforcement initiative, because in Brazil, when they detect a new deforested area, INPE gives this area to enforcement on the ground, to forces interventions on the ground. And this system is co-developed with local experts at INPE. So, for the sake of comparison, regarding global system products such as RAD or Global Forest Watch, for example, in a global system, we have maps and alerts with balanced commission and omission metrics, which is very common. But for the needs of Brazil, we need zero commission error. We need zero false detections. Why? Because we can't send forces interventions on the ground if we are wrong in our detection. So in this case, when you have intervention on the ground, it's better to detect only, say, for example, 50% of the deforestations, but with zero or near zero false detection. In the global alert system, we usually have a fixed sensitivity to backscatter anomalies, whereas in general, local authorities need a sensitivity of the system changing with forest characteristics. And when we use such alerts on the ground, you don't need raster files, but you need vector files that are very easy to integrate in operation system on the ground. So in general, we need a modular and customized detection, and the last mile, what we call the last mile, it's really the last steps of the deforestation detection should be performed by the local authorities using ready to analyze raster or even better vector files. The local knowledge and expert insights are included in the process, and we need an horizontal and optimized collaboration frameworks. So this is illustrated in this slide. So you have data acquisition here. We wrote SAR data, but of course it can be SAR and optical data. And we need we need HPC computers or cloud computing to be able to process all these satellite images and to pre-process all this detection, and then the fine-tuning detections, deforestation detection, should be done by local experts who know their forests, who know their needs. So that's why there is no development of such system without any cooperation. And here is the final slide about our cooperation with Brazil. So we process all the big data, all these images at CNES, and then INPE do the last mile, and do the deforestation detections on site, and then send the results to the forces of intervention forces. Of course, this system can be applied to other types of forest. So I was talking mostly about dense forest, dense forest in the tropics, in Amazonia, in Africa, and in Southeast Asia. But we also apply this system to temperate forests. So I won't be long on this because most of you are not very interested in temperate forests, but just to say that it can be adapted to other kind of forests. Temperate forests are, of course, of importance because they sequester a lot of greenhouse gas emissions in the world. This is a refuge of rich biodiversity as well, and this is a major economic resource, and it will be even more an economic resource in the future. With there is a great pressure on temperate forests right now, and so they are under threat. Also, due to the climate change, we have drought, we have heat waves, we have pest infestations, disease, and however, there is limited information regarding the current status of such forests in Europe, for example. So this is hello?
Yes.
Can you hear me?
Yes.
Okay,
Very
sorry, I
nice.
think I lost you. So you can see that that, for example, we adapted our tropical dense forest detection method, taking into account, for example, snow in temperate forest and so on, to adapt our methods and then to detect clear cuts in mainland France. So this is all the reference data we used. In red, you have forest clear cuts reference data and forest dieback reference data in yellow. We took into account the FAO forest definition because France consider these definitions for its forests. And then we could map a clear-cut density in mainland France. On the left-hand part, you have a broadleaf clear-cut density, and in the right-hand part, you have conifer clear-cut density. So just to say that we can separate the detection for different kind of forests. Here you have some zoom in of some forests in France. So here at the top you have conifers in the land forests, in the land regions, and you have also clear cuts in public forests. This is number 2. You have poplar clear cuts, number 3, not so far from Paris, and also clear cuts in mountain forests. So I know that in Africa, for example, you have there are countries with a mountain forest. So the detection system also works in forests in steep slopes. And we can, of course, assess some statistic per regions, but also per types of forest along the years from 2018 to 2040. And you can see the distribution of conifer and broadleaf forest depending on the regions. So this is this kind of statistic are of importance for some stakeholders. And here in these figures, you can see that we really can see the temporal evolution of clear cuts that we do as well, of course, in the tropics along the month and the seasons. And for example, this temporal evolution here is completely logical, and this has been validated by some foresters in France. For example, in winter, you don't have a lot of clear cuts because sometimes it's snowy, sometimes it's very wet, the weather is not adapted. So, and then we have much more clear cuts at the beginning of the summertime and along the summer. And of course, you can also assess clear cuts depending of different forest tree species. You can see here maritime pine in front and spruce, poplar, and so on. So we also can adapt our deforestation detection systems in open forests, such as savannas. So this is very important, of course. Why? Because we have a lot of degradations in savanna, and also in particular because there are almost no detection systems in savanna. There is one actually, which is called Luca, developed by CETRIS, but the system is not open. You cannot, for example, you cannot download the files. This is not an open system. You can see here in the middle a Thuy Le Toan. It's a bit small, but you can recognize the Thuy Le Toan in South Africa, and myself actually. So it was this photo is in the Kruger National Park in South Africa. So here we are talking about low biomass areas, which are any kind of mixed tree grass ecosystems, including woodlands and dry forests. Of course, savanna are very recognized for their essential ecosystem services. They are very relevant in South Africa and Africa. They are huge, actually. And savanna, for example, in Africa, constitute approximately half of the total above ground carbon. So it's huge. It's a huge amount of carbon in Africa. And they are currently impacted by anthropogenic activities such as afforestation and deforestation. And deforestation rates in African savanna are even higher than those in tropical rainforest. This is a forest biomass maps in savannas, for example, here in Africa and here in the Cerrado, that we published few years ago with CESBIO. This is in the range 0 to 100 tons per hectare. So in low biomass areas, especially in savannas, it was derived with Allospalsa. And so this is an example of a tiger bush in Sudan, actually, which is very beautiful to see. You have very regular patterns, and we can see them because we have a spatial resolution of 25 meter pixel size. And of course, this map was validated with LiDAR dataset. So here you have some example in South Africa. You have LiDAR-based biomass dataset on the left and our map on the right. And the map was actually providing very accurate biomass estimations. And why I'm talking about biomass here is just to say that in low biomass areas, what we call non-forest areas, so below the like the forest definitions of the countries, we have sometimes a great proportion of carbon stocks in these non-forest area. Maybe I can take just an example of Mozambique. Here we took the tree cover from Hansen et al. 2013, and we took the forest definition of Mozambique, which is this is a pink dot, 30% tree cover, and you can see that all the forest below 30% of tree cover, so like what is considered as non-forest area, represents half of the total biomass stocks of Mozambique. And you can see that in Kenya, for example, there is a huge amount of carbon stock that is located in non-forest area, because there is a great amount of drylands in this country with carbon stocks. So to tackle this problem, to detect degradation in such low biomass areas, in our opinion, it's better to combine radar and optical data. Why? Because we showed that, first of all, the use of radar and optical data together increase the accuracy of deforestation systems, and also because optical images together with radar images works well in savannas. So our advice and what we are doing is to use all the inputs like Sentinel-1, Sentinel-2, and why not other sensors such as biomass and NISA used to get as inputs of one detection method to produce deforestation alerts. Why? Because usually people derived different detection methods with Sentinel-1 as inputs or Sentinel-2 as inputs and so on, and then they merge the results, and it leads to a lot of discrepancies in the results. For example, usually they use union or intersections of different alert systems, and then we have huge omissions alerts, for example, of commissions error. So it's better to fuse the inputs and to use one detection method. So this was the topic of PhD study from Marta Botani. I'm talking about Marta because because we supervised her PhD, and because this is a new alert system dedicated to dense forest and to savannas. So she tried her new system based on Sentinel-1 and Sentinel-2 images over the Cerrado, in addition to Amazonia. And she showed that using both Sentinel-1 and Sentinel-2 images, which is here illustrated in what is called MS, multi-source BOCD. BOCD is the name of her system. And she compared this with radar-only BOCD, which is called VH, or RAD, or Global Forest Watch, and so on. And she got she got better omission results. And what is not shown here is that she has much less false alarms. So it's better, in our opinion, to use both radar and optical images in savannas. And last but not least, and Thuy will talk about in the next talk, we can, of course, consider both deforestation detections and biomass maps. So here in this example, we used the biomass maps from the Climate Change Initiative from ESA, the CCI biomass maps in Cambodia. And then we assessed carbon loss over the areas that we detected as deforested, and we could assess the carbon loss in time in Cambodia, but also in French Guiana, in Gabon, and so on. Of course, this can we did that with biomass maps, but from the Climate Change Initiative. But of course, now we have the biomass missions presented by Thuy Le Toan in a few minutes, and we can use also the NISA sensor from the NASA and ISRO that has been launched as well this year. You can use GDI LiDAR on the ISS, Sentinel-1, Sentinel-2 to increase the forest biomass estimation, forest height estimation, and deforestation detection. So now we have a bunch of different sensors to increase the accuracy of all this system. And here are some few images of illustrating our cooperations with some countries. Here, for example, a trip in Cambodia that we've done with Thuy. Here you can see Alexandre Bouvet as well, and some Cambodian partners. Here you can see Thuy crossing a river. And here deforestation in Cambodia, and a few other images. On the ground in French Guiana. Here it's a picture of ONF in French Guiana as well. A picture of Juan Doblas in Amazonia, and a picture of myself with here Alexandre Bouvet in Brazil. All these methods these results have been validated and have been published in some papers that you can consult. So most of these papers are free online, so you can consult most of these papers on the internet without paying anything. And to summarize this talk, the take-home message is that this system is operational. It can be used, for example, for international agreements. It's being adapted to savannas, and it can be extended to any country as long as we cooperate with them and as long as we use their forest definition. So we use their forest masks. We need to work with people locally. You have here the website of TropiSCO. And if you have any questions that I can't or I don't have the time to answer today, you can write to myself or also to Thierry Colec, which is like my CNES partner, working a lot with TropiSCO. And maybe if I have 2 or 3 more minutes, I can show you the CNES platform. So you stop me, Cecilia or Linda, if you...
No, it's fine. You have
Okay.
5 minutes.
Okay, so just in 2 minutes, here it's the TropiSCO website that anyone can browse in because it's open to anyone. You have several countries that have been mapped. So countries, as I said, in Southeast Asia, in South America, here in Brazil, and also, for example, in Africa, we have Gabon. You can zoom in here. In the background, we have a Sentinel-2 mosaic, on an annual mosaic. Of course, in Gabon, we have many clouds, and you can see here our detections in yellow appearing in time. So in yellow, you have detection in 2018, and then you have the temporal evolution of the detection from yellow to orange and red. So from 2018 to now, actually, because the system is operational. So and of course you can zoom in more, and here you can see forest exploitation with a forest kind of road on the ground. You can compare with GLAD. Here we have many a few detection of GLAD, but you can compare. If you zoom out, you have some statistics of the country. You have statistic per region, actually. Sorry, I will switch in English. So you have statistic per region and for the whole countries. So here you have forest loss since 2018 per year, but you have also per month, and you can select, for example, a year. So you can see here you have a more deforestation in July, August, and so on. And you have also statistic on carbon loss, because we crossed our deforestation detections with the CCI, the Climate Change Initiative biomass maps from ESA. And you can also download this data, so you can see here. And you have here all the raster files per country and per year, and you have some explanations on the method. You have also WMS flux, and you have also information on the methods, the papers, and so on. So I think I'm done. So I thank you very much, and feel free if you have any questions.
Thank you very much, Stéphane, for this very interesting and very clear presentation. I can see that we have already questions in the chat. So first, we have a question from Mr. Joshua Nyakundi. In fact, there are many questions related to the cooperation possibilities and how does it work and so on. The question also from Tanzania related to how to cooperate with you, and also from Cameroon. So, can you see the question in the chat, Stéphane?
Yes. So thank you very much, everyone, for the question. I mean, regarding cooperation, usually we set up a first remote meeting, a visio, together with you and with CNES and with usually myself and colleagues to to set up a first meeting, discuss your needs, the problematic of your country, discuss the specificities of your forest, because of course you know your forest much better than we know. And so yes, usually we set up a first contact, first visio, and then we discuss. What are the limits of the methodologies? There are many. No, this is not very biomass density limited, but for example, some limitations. First of all, our system right now is mainly based on Sentinel-1, so which is very nice actually, especially in tropical countries. But as you can see, we developed only recently a system based on both SAR and optical data. So we fixed this problem, but this is kind of recent. So to do this, we use the system from Marta Botani that I showed you. Is based on a Bayesian algorithm, but you could use, of course, artificial intelligence or other machine learning system. We could, of course, improve the accuracy using more satellites, as I said, like biomass, NISA. So we could improve the accuracy using more inputs. We could also improve the spatial resolution or the minimum mapping unit of the system. The minimum mapping unit is 0.1 hectare. It's not enough to detect small detections such as selective logging, for example. So research is going on, but I think this is one of the limitations of our system. So you can see that there are many. This is ongoing research. So many ideas and work to be done again.
Okay, thank you, Stéphane.
For mangrove, I'm not sure, because with radar data, it's more tricky because as you know, probably if you know mangrove, you have the problem of the tide. You have tide, and when you have water or no water under the forest, it can create some temporal evolution on the backscatter, and so it's not easy on mangrove. So I'm not sure for mangrove. So yes, sorry.
I'll let you read the question. I think it's better if you read the question yourself.
Okay. Yes, we collaborate with some NGOs. So, for example, we collaborate with WWF. We collaborate with Greenpeace. So we collaborate with some NGOs. And regarding building capacity, so I'm personally Stéphane Mermoz in a private company called GLOBEO, and one of our mission is to provide some transfer capacity. So we provide sometimes some formation in different frameworks. So yes, we we do that sometimes. And I thank you for the very positive, like the positive feedbacks. Very like thank you, Kelvin, for example, or Agnes. It's very nice of you.
There's a technical question regarding your platform. Does it provide API? For example, if one needs to integrate to another platform?
Not really. I mean, until now, you can use, for example, a WMS Flux, but there is no really not a real API. But it's under discussion actually, because there is really a need with API. So actually there is such a need of deforestation alerts with, for example, the new law, European law, the EUDR law, and so on, or conservation agreements, that it's really under discussion.
Okay, and then we have 3 last question in the chat. Are you collaborating with partners in Tanzania?
No.
Not okay.
No.
And one question regarding training. Do you have any plans to train users to use this system?
I mean, if we have a framework, of course it can be done, and we already did that with the frame of TropiSCO in the past, and of course it could be organized. I mean, we just need a framework. Yes.
And the last question regarding your plans for sub-Saharan countries.
We would like to very much. We would like to very much. We are discussing with some countries right now, so it's also under discussion, and we would love to. Actually, we would like to extend this system to more countries, and especially I mean, in some countries with dense forest, but also in some countries with savannas, where, as I said, there is very limited solutions. Actually, there are almost no solutions. There is Global Forest Watch, but it's annual, and as you know, in open forest, it's really, I mean, the accuracy is very low. It's very difficult to use and almost impossible.
Okay, so I can see there's an interest also from a private company to cooperate with you. So you feel free to get in touch with Stéphane, because you have his address in the slides. I thank you very much, Stéphane. I think it's time now to go on with the next presentation. Thank also to all the participants for their questions. And now I propose to let the floor to Thuy.
Thank you very much.
Thank you, Stéphane.
Okay, so you shut the partage, okay?
Yes.
Okay, partage. Okay. Can you see my slide? Yes?
Yes.
Okay. I am Thuy Le Toan. I am from CESBIO, a research lab in Toulouse, France. But I participate now in the activity of GLOBEO. As you can see, that GLOBEO now is on the operational side, and at CESBIO we are doing research and development. So this is an introduction to the biomass mission, because we are still 6 months after the launch of the satellite, so not much result will be shown here. Okay, so I will start with some common knowledge that some of you may know already, but it's just to recall that why it is important to observe the forest. You have seen the deforestation by Stéphane, but this because the forest cover 31% of the Earth's surface, and 1.6 billion people depend on them for their livelihoods. And wood is the primary source of energy for approximately 2.6 billion people. And forests are the largest reservoir of biodiversity and contain more than 2/3 of all terrestrial life. Here the illustration. But we talk about the forest today because of it's a major role in maintaining balances in the global cycles. For carbon cycle, forests store more than half of the carbon on the land surface and play a crucial role in regulating atmospheric CO2. And in forests also involved in the water cycle and water quality. And these major roles of the forest are threatened by human activity and climate change. Human activity was about deforestation, degradation, overexploitation that the TropiSCO talk about. And climate change produce drought, fire, storm, pest infestation, etc. And those will lead to harmful effects on the climate, reduce carbon absorption and evapotranspiration, increase carbon emission and albedo, which in turn contribute to climate change. And not last but not least, on the services provided by the forest ecosystem, depletion of resources, loss of biodiversity, destruction of species, habitat, and increased risk of endemic disease. Sequestration of carbon by forest contributes to mitigation human-induced climate change. Okay, so here the forest is the carbon sink because photosynthesis in the trees convert the mineral carbon from atmospheric CO2 into organic carbon. And in the forest, the major parts of organic carbon is stored in above-ground living biomass and underground living biomass. And when the forests reach the climate state and manage to renew themselves, the carbon sequestration reaches a plateau of lasting stability and even gradually increase over time. So people, the knowledge when we learn at school is that tropical forest is a stable system. The photosynthesis minus plant respiration is quite stable, and it is a sustainable sink of carbon dioxide. But now with the later on you will see that the deforestation, etc., will disturb this stability. And for example, in the primary forests of the Congo Basin, it was thought that the forest sequesters 600 million tons, which represent about 1/3 of the CO2 emission generated by the entire transportation sector in the United States, so that people use the forest to have other source of to compensate other source of carbon emission. Okay. But the forest, as I say, can change from carbon sink to carbon source caused by disturbance. When human intervention, notably deforestation, interrupt the photosynthesis and respiration cycles of trees, causing the carbon stored in the forest to escape atmospheric CO2. And this, for example, why the Amazon basin still constitutes a net carbon sink, the rate of deforestation in the last decades threaten to transform it into a source of CO2 emission. And globally, 1/5 of the greenhouse gas emission from human activities come from forest destruction. And that's why all the international convention and agreement and national determination on the forest aim at reducing the carbon emission, increasing carbon sequestration, and for example, the REDD+. And for that, we need to quantify the carbon losses and gain. Okay. What is REDD+, and how does it work to reduce greenhouse gas? REDD+, here you can see reduction emission from deforestation and forest degradation, plus the plus is a conservation of forests, sustainable management of forests, and enhancement of forest carbon stock. And this is for the remote sensing people, but most of you know about that the REDD+ action can lead to financial incentive called result-based payment. And to implement this result-based payment, there's a need for a robust and transparent national forest monitoring system that provide MRV. And the remote sensing is a key tool for MRV, as it can provide robust and transparent estimate of deforestation and carbon stock change. I cannot. Okay. And here that's why at the COP 30 in Belém running right now, the forest protection tops the climate agenda. Here you can see the forest is the hottest topic presently. And why measuring forest biomass for quantifying carbon loss and gain? Biomass consists of approximately 50% of carbon, and forests account for 70–90% of terrestrial above-ground biomass, and the majority are located in the tropics. And the forest biomass stock and their change remain right now poorly quantified. Here, biomass driveway of woody matters in tons per hectare. Right now, measured by measuring diameters of the tree, the height of the trees, and knowing the species of the trees, we use allometric equation to relate those parameters to the biomass of the trees. And this for a certain number of trees, and in inventory, plot inventory and national inventory. And current approach to estimation of carbon emission by forest are estimated from the change in biomass and the change in the impact area. For deforestation, the change in carbon is the product of impact area by the biomass of some site or regional location, and multiplied by an efficiency factor. It's very vague factor depending on forest ecosystem. And for forest degradation, we need the forest area remain the same, but the biomass change. And currently, this is done by National Forest Inventory. But the crucial information we need is in the tropics. Why? Because of carbon sequestration depend on the forest ecosystem. And here the figures show the amount of carbon stored in terrestrial ecosystem. You have tropical wet forest, tropical moist forest, tropical dry, tropical mountain, temperate warm, temperate dry, temperate moist, etc., and boreal, and boreal moist and dry. So we can see that the tropical forest contain sequester more carbon than other ecosystems because they benefit from sunlight, abundant rainfall, and so the volume of their biomass and their carbon stock are more important. For example, on average, people think that the carbon per hectare in the tropical biomass is about 120 tons of carbon, and whereas temperate forests store only 57 is from some measurement. But the high biomass tropical forest is a challenge for measuring system. There's a lack of forest inventory in tropical forest, is the financial access condition, etc. And the high range of biomass represent a challenge for most remote sensing systems. Optical, high-frequency SAR data, spaceborne LiDAR, and yet the HGB about carbon biomass in this range are necessary to reduce uncertainty in carbon stock and carbon losses due to deforestation and forest degradation. We know that deforestation sometimes happens in area with high carbon and high biomass. And if we make error in the biomass of this deforested area, and the budget of the carbon budget will have very large uncertainties. Okay, there's another thing is in tropical forest, difficulties to quantifying underlying topography, which is needed in forest ecology, biodiversity, hydrology, etc. Here you can see an image of multi-layer structure with dense canopy and few emerging trees, which store a great part of biomass. So that's why when we do, for example, LiDAR data on many footprints, and the mean value of the height is not changed much with some few emerging trees, but it changes the biomass. In this context, 20 years ago, we proposed to ESA a satellite mission for mapping forest carbon from space. And this, where we can see that here that the proposal, here the science team proposing this project, and myself and Sean Cregan. And then after many years, now 20 years, the final selection is on May 2013, and the launch is now in April 2025, so 25 years. In between, there are a lot of work by the scientific communities and by industry. And in this proposal, we propose to deliver products defined to meet the carbon information requirement. 3 kinds of products: forest biomass in tons per hectare, forest height, upper canopy height, and disturbance area of forest clearing. And then in the global carbon information requirement, we need hectare resolution. We need 1 map, 2 maps per year for 4 years, because it was the minimum for lifetime for a satellite. But now biomass will last longer. And global coverage of forested area, accuracy of the product will be 20% or 10 tons per hectare for biomass lower than 50 tons per hectare. Upper canopy height, the same thing. and for area of forest clearing, 50 to 50 meters resolution, and one map every 6 months, and global coverage and 90% classification accuracy. This was the requirement. And here, before the launch, here the summary of the project of the biomass mission by the consortium of industry and Airbus. Here, forest is the reason the forest act as carbon sink. Here you have the detail here. And forest land use release carbon, and we use the P-band radar to measure the amount of biomass and carbon stored in the forest. And this will be for the first time at the global scale. And why we define the radar in long wavelength radar to measure biomass. Mapping forest biomass require a radar sensor with long wavelength to penetrate the canopy in all forest biome, to go from the top to the bottom, even for forests at 40, 50 meters high. And to interact with the vegetation element. Because if we interact with the leaf and the small twigs, then saturation comes very, very early. And if we can interact only with woody vegetation element, we will have strong relationship between our measurement and biomass, about our biomass. And also so that forest height can be estimated with a single satellite. Both biomass and forest height can be estimated by a single satellite, because in order to have the forest height using other lower wavelength, the moving of a small element of the trees degrade the correlation between signal. And this we conclude that this implied a radar at P-band of wavelength about 70 centimeters, and the longest possible from space. And okay, here this illustrates why and what radar system for forest biomass. So we can have here the Austrian vine. X-band, we see the needle. C-band, see needle with small teeth. N-band, see this way. And the P-band, you see the big branches and the drum. And so, because above ground biomass is measured mostly using the stem or the trunk biomass, and so we have more direct relation with above ground biomass. Or here is a bit nice graph done by Airbus about X-band, C-band, N-band, and P-band. That's one thing. Also, the saturation is very early when complete closure, like opticon. C-band penetrate a bit in the canopy, N-band also, but the N-band saturate at 100, 150 tons per hectare. And the P-band, we expect that this is with saturate much longer, larger biomass. And so we conduct the airborne campaign to assess the potential of P-band SAR. And it was a campaign in the past in many places in the world, here in France, USA, Colombia, Costa Rica, Sweden. And we have something like this with only P-band one polarization, HV, cross polarization backscatter. And it was based on this one that the mission has been selected here in the map of the biomass of land forest in France. And then when we go to higher biomass, higher than 250 tons, up to 500 tons, we have the sensitivity of the CNES to biomass is reduced. And so we need to have a way to retrieve the sensitivity of biomass from the radar. So we use now 3 techniques to enhance estimation of above ground biomass. POLSAR is a polarimetry SAR. Here you have the illustration. We have a map, 2-dimension map. And POL-INSAR, interferometry SAR polarimetric. And using the plus the height and the backscatter intensity and height, having this kind of presentation. And now the newest technique is the TOMOSAR, tomography SAR, to have a different slide of the forest. It's a multi 3D structure of the forest. And here, this innovative SAR tomography has been applied to map 3D structure of forest. Here, the system flies many times over a given point with orbit, a small shape of orbit here for biomass every 3 days, 7 orbit. And then we, from the stock of image, got obtained from each acquisition. There's a tomography processing to deliver the here on the bottom the different layer of the forest, in different height, and then illustrated that way here. From this is a SAR image, HV original image. We tomography from A to A prime, and we look at the 3D structure of this from this one to this one, and we can see the height. We can see the ground layer and different layer of the forest with different trees, and they are different from HH, HV, and VV channel. So this was to construct the 3D structure of the forest and to estimate the AGB about our biomass up to 500 tons per hectare. Here, I plot, I show figures of the forest with TOMOSAR resolution. For example, here for resolution cell, and then the SAR, original SAR, is the resolution cell encompass all the 4 cells. And then if first we think that if we take the bottom cell, it will be related to biomass because it will see only the trunk of the forest. But we discovered that this cell in the bottom contain also the backscatter from the ground. So it's disturb the sensitivity. If, for example, here the original image HV and the layer 0 at 0 meters, and you have a bit of sensitivity, but very small. And if we took 15 meters, you have something like this. But if you take this, something in the range of 20 to 30 to 40 meters, then you will not have the effect of the ground return. And ecologically, in this part, this layer contain most of the big branches, and those are related to the above ground biomass, because what information, reference information we have is about cow biomass of the 3 tons from the top to the bottom, and plus the branches. And why? And we have discovered that the biomass of this layer is related to the total biomass. And so we isolate this layer here at 30 meters, and we map the biomass of the French Guiana up to here 500 tons per hectare. Okay, and so there's intense and varied activities conducted by scientific communities and industry. This show the members of Biomass Mission Advisory Group to Airbus. We have about 10%, and here is we look at the assembly of the satellite. It's what in Airbus in Toulouse. And among the activities, GeoTrees established in situ biomass reference measurement site in order to have the training and calibration and validation of the product. And here the existing forest plot in GeoTrees in yellow, and black is the plan establishment of the forest plot. You can see that there are few in Africa, and there are not much in here in Southeast Asia, and much more in South America. And GeoTrees is established through collaboration with existing international networks of high-quality, long-term monitoring forest plot using by ecologists that use standard forest monitoring protocol. So you can, if you are interested, go to the website, the GeoTrees website. And here we go to a summary of the biomass mission, the problem. Okay, biomass is concentrated in the tropic, 31% of land surface, and the tropical for biomass have a big uncertainty, a big range, and also big amount of tons with uncertainty due to low number of measurement and current estimation based on tree allometry. Solution, systematic measurement of biomass from space. Okay, mission first proposed in 2005. And the objective is to provide consistent, accurate, global scale measurement of biomass. And it was selected as Earth Explorer 7 by ESA in Graz, Austria in 2013. And biomass is a fully polarimetric synthetic aperture radar mission, HH, HV, return, pulsar, and tomography techniques. Implementation, Airbus consortium, again, the biomass mission, industrial implementation. Okay, you have the industrial, and they have summary of 3 continents, 26 countries, 42 contractors, more than 1,200 people in the development of the biomass mission in the industrial side. And now we went to the launch of biomass on 29th April this year from Kourou, French Guiana. Here you have the YouTube to watch the, and here I has been interviewed after the launch. And now I will show just the first biomass images, because we are still in the Kanban process, and the data will be released to public soon after validation of the data. And now ESA released a few images to show the possibility of biomass. And this show a first image in northern Brazil. Here the tricolor for HHVV and HV. And here you can see that along the river there are trees. And here is the trees, but biomass penetrate inside the canopy and reveal the wetland water under the canopy. And here the green one is forest. And the topography will be seen very clearly. They are covered by forest, by thick forest, but using biomass, there's penetration, so you can detect the tomography. Another example in Bolivia, okay, it's the same thing, but we can detect grassland and other vegetation type and forest type. And then, for example, in Opticon, the grassland and other vegetation sometimes are quite similar. And there is an image of Indonesia. Indonesia, here you can see volcano and topography and wetland, etc. And also feature in the sea that we have to discover. And here the view of the desert. Desert is the land desert in Chad, the Tibesti mountains in the Central Sahara. You see, if you take an image in Opticon, it's on white, on yellow. And here you see a lot of things. So subsurface geology feature in desert. So I think that a lot of work will be done by by scientists for the subsurface in Sahara and everywhere. The same penetration in the ice, because the wave cannot penetrate into the ice when it can penetrate into the ice because of the water molecule in the ice are blocked, so they cannot move, and so it can penetrate and here you can detect something that you cannot see with optical data, and so it's the internal structure of the ice. These are the capacity that opticon or shorter wavelength cannot achieve. Okay, so some work on the update on biomass data status. We are still in the commissioning phase, initial 6 months, and the end it was decided for 21st of November in 1 week from now. And after that, there will be a tomographic phase, TOMOSA, for the first 14 months, or now 15 or 16 months. And during the TOM phase, an interferometric stack of 7 images will be collected for each one. And after this period, there will be a global coverage of TOMOSA. But if you are lucky, your site could be covered by TOMOSA very early during the first 14 or 15 months. And then after the tomographic phase, the interferometric phase for the remaining time of the mission, 5-year duration. And then an interferometric stack of 3 images will be collected for each one within the interferometric acquisition mass, 5 global coverage. Update, and we will have a conference, Bon-ISAR and Biomass conference in January in Slovenia. Here you can go to the website to see the conference. And during this conference, the ESA will inform the community about the mission status and first reason on instrument performance, Fourth reason on PBANSA over forest, IDGEO, ocean, and ionosphere. And review of the state of cloud-based forest validation activity, review of the state of Kanban activities, review preparatory activities on the integration of biomass in carbon modeling and policy activity. And this will lead to the public release of biomass data. And you have two things different, biomass data and biomass product. Biomass data directly from biomass after calibration, validation, etc. And the product is the data transformed into the height, into biomass, into the disturbance area, and duly validated before to be released. Okay, thank you very much for your attention. Okay.
Okay. Thank you. Thank you very much, Thuy, for this very comprehensive presentation, covering all the challenges related to biomass monitoring, and also the presentation of this very advanced mission called also Biomass, and developed by ESA. Upon an idea that was proposed by you 20 years ago. So we can see that it takes a very, very long time to develop a space mission.
Yeah. You need to be younger to propose the mission.
You are always young. Okay, so are there any questions? Sorry, the webinar, it took a little bit longer than what was planned. So I can see that some people, they could not stay until the end, but hopefully most of the audience has stayed connected.
Okay, if you have question, and then you can write it to me afterwards.
Yes, so you can write to Thuy directly if you have questions after the webinar, or okay, you feel free to speak also and to intervene.
Okay, so I can reply to the question. Okay, what is the below ground biomass? We cannot have the below ground biomass, but we now in the plot, in the reference plot, we use allometric equation to relate the above ground plot to the below ground above ground biomass to below ground biomass, and this is what we are doing right now. Yeah. And the below ground biomass usually is very much related to the above ground biomass, and it will not affect the overall estimation, because in the forest, the floor of the forest is always wet. It's about at least 20% water content, and so the penetration will be as much as in the desert or in the ice. Okay, that is okay for you.
Does it answer your question?
There was a question about below ground biomass.
Yes. I can see you, Mr. Kelvin Washira from Kenya. Okay, so I guess the presentation, it was much appreciated from the audience. Yes, so the answer, okay.
I don't know where. The question.
Okay, so that's someone thanking you for influencing his research on to the use of SAR for rice. Maybe we will have a webinar dedicated to rice monitoring.
Yes, and also in I think in a year from now we could think to have a webinar on the result and how to use the data really. And because we are still in research and development, but in 1 year or 2 years, we hope to go to at least for pieces for local forests, or to have something which could be operational. And then we can also make another webinar in detail. Okay, so my research journey in the use of SAP for high research in Nigeria. Okay, thank you very much. I'm Shamaka. Yeah, I make a webinar on rice, and there was more than 300 people following. And so it's okay, the one of the rice researcher in Nigeria. So it's very nice. Thank you.
Okay, so it was a rather long webinar, so I'm proposing to stop now. So thanks again to our speakers, Thuy, Stéphane also. It was a we have a very nice overview of all the techniques to monitor forest based on remote sensing data. So next webinar will take place December 5th. I guess what day will it be? It will be on Friday. Friday 5th of December, and it will be dedicated to hydrology also in Africa, and we will have the participation of Professor Jean-François Créteau from Lagos and Paul Spetcom also. And now they are in Cameroon right now because they are delivering training for I would not a summer school, but almost winter school or autumn school. Yes, so they will inform us about the outcomes of this school, these training sessions, and also the techniques for hydrology based on remote sensing data. Okay, so thanks to all for your participation. See you soon, and have a nice day. Thanks again.
Okay, thank you. Thank
Bye.
you.
Thank you very much.
Thank you.
Bye-bye.
Goodbye. And we will share the presentation with you.
Okay.
Thank you.